Suppose we have a segment of wire with electric current flowing through that wire. And we want to find the magnitude and direction of the magnetic field created by this current. So if we have a differential charge element along this wire, being dq, and recall that this is the magnetic field that we derived due to a single point charge traveling at some velocity at a point at some distance away from the charge. So we have the differential magnetic field due to a differential charge is equal to the magnetic permeability on 4 pi by dq, but the velocity of the differential charge cross r hat on r squared. So if we suppose this is a differential charge element that's traveling at some velocity in the direction of the current, and we have a radial vector to the point where we're finding the magnetic field. So the unit vector, r hat, is a radial vector normalized by its magnitude. Now if we take the differential charge on dt by dt, then dq dt is the current, and the velocity by dt is a differential distance that the charge travels over that infinitesimal time interval, which will denote dl, being the differential length along that wire. So we can replace this now with the current by dl. And therefore the magnitude of the differential magnetic field is the magnetic permeability on 4 pi by the current. So dl cross r hat is the magnitude of dl by the magnitude of r hat, which is 1, by sine of the angle between the two vectors on r squared. So this here is the Biot-Savart law in vector and scalar form, which allows us to obtain the magnitude and direction of a magnetic field created by an electric current. So in this case, by the right hand rule, dl cross r hat will give us a magnetic field that's pointing out of the screen, or towards the positive x direction. And if we integrate this along the length of the wire, then we obtain a net magnetic field due to the current in this wire. Recall the Biot-Savart law, which allows us to determine the magnetic field due to a current flowing through a wire or a conductor. So it depends on a magnetic permeability on 4 pi by the current in that wire by the differential length along the wire cross r hat, which is a unit vector of the radial vector to the point where we're determining the differential magnetic field due to the differential charge along this differential length. So that's divided by r squared, being the squared distance from the differential charge to the point where we're determining the magnetic field. So in this case, the wire is positioned along the positive y-axis. So dl cross r hat, being this unit vector, by the right hand rule will give us a differential magnetic field that points in the positive x direction, or out of the screen. Now if we look at the wire from the positive y-axis, then we're going to see it as a point with a circle around it. So this is the convention that we adopt, where the current is flowing out of the screen. So this here is the positive y direction that we're looking from. So as we can see, the magnetic field vector points in the positive x direction. So if we're looking at the magnetic field vector from this direction, then we're going to see it pointing to our left. So the magnetic field lines at some radial distance from this differential charge are drawn in the anti-clockwise direction. So the magnetic field vector is tangent to these magnetic field lines. So this is just a convention, but of course the magnetic field lines are going to be drawn further apart as we go further out from this wire, because the magnetic field drops off with the square of the radial distance. So therefore we can determine the direction of the magnetic field using the right-hand rule, where in this case the current is flowing out of the screen. So your thumb points in the direction of the current, and then curling your fingers gives you the direction of the magnetic field. So if instead we're looking from the back of the wire, then the current is going to flow into the screen, and the magnetic field lines are going to be clockwise in this case. So as you can imagine, this magnetic field vector will be pointing to our right. So note that in this case, we're looking at the magnetic field around a small segment of current carrying wire, and the magnetic field vectors are tangent to these concentric circles that are centered on the wire. And the direction of the magnetic field is determined by the direction of the current and the right-hand rule. So the magnetic field has no component away from the wire or parallel to the segment of the current carrying wire. Recall that the magnetic force acting on a charge which is traveling at some velocity in a magnetic field is Q by the velocity cross B. Now suppose we have a wire in a magnetic field, then a differential charge on that wire will experience a differential magnetic force. And again, if we take dq dt by dt, then we get the current multiplied by V dt. And V dt is the differential length that the charge travels along the wire. So we can rewrite this differential force as the current by dl cross B. And if we integrate both sides, we obtain a total force exerted on that wire due to this magnetic field. So for example, suppose we have this wire inside this magnetic field with a current going through this wire, then the differential length of wire is going to have a magnetic field vector at this point pointing out of the screen into the x-axis. So by the right hand rule, dl cross b is going to result in a magnetic force vector that's pulling downwards on that wire at this location. And then if we integrate along the length of the wire, we obtain a net force exerted on the wire due to this magnetic field. So again, we obtain a direction of the force using the right hand rule. And note that if the current in the wire is 0, then there will be no moving charge, and therefore no force exerted by the magnetic field on this wire. Because magnetic fields only exert forces on moving charges. Let's find the magnitude and direction of the magnetic field at the center of this loop of wire. And suppose the current is going anti-clockwise. So recall the Biot-Savart law and the differential magnetic field being equal to the magnetic permeability on 4 pi by the current by the differential length along the wire cross r hat, which is a radial vector from this point to the point where we're determining the magnetic field, normalized by its magnitude. And that's divided by r squared. So the scalar version is the magnitude of the differential magnetic field is the magnetic permeability on 4 pi by the current by the magnitude of dl by the magnitude of r hat, which is 1 sine theta on r squared. So using the geometry of this problem, if we take this as our differential angle and the radius of this circular loop as r, then the differential length is r d theta. And theta, being the angle between dl and r hat, is always 90 degrees. So sine pi on 2 is always 1. So therefore our differential magnetic field is a magnetic permeability on 4 pi by the current by r d theta on r squared. So therefore we can simplify this to mu naught I on 4 pi r d theta, and then if we integrate both sides, we get the total magnetic field at the center of this wire. So all of these quantities are constant, so we can take them outside the integral, and we integrate from 0 to 2 pi. So what we get is a magnetic permeability by I by 2 pi on 4 pi r. So therefore the magnitude of the magnetic field vector is mu naught by I on 2r. And because the current is flowing anti-clockwise, then dl cross r hat by the right hand rule is going to result in a magnetic field vector that points out of the plane. So that's the direction of our magnetic field. Let's find a magnetic field at a point along the perpendicular bisector of an infinitely long wire carrying a current I. So if we take a differential length vector along this wire, dl, and a radial vector to this point along the bisector, then the unit vector to this point we denote r hat, and the angle between these vectors is theta. So if we take the cross product between dl and r, by the right hand rule, our differential magnetic field vector points out of the plane. So recall the Biot-Savart law, which gives dB is the magnetic permeability on 4 pi by the current by dl cross r hat on r squared. So this problem is symmetric because if you did the same thing on this side of the wire, you're going to get a differential magnetic field vector with the same magnitude pointing out of the plane. So I'll leave that part for you as an exercise. So if we denote L being the length vector from the perpendicular bisector to this element, we're going to integrate from 0 to the infinite length of the wire due to the symmetry of the problem. So writing the Biot-Savart law in magnitude form, we have the magnetic permeability by I on 4 pi by dl being the magnitude of this differential length vector by the magnitude of r hat, which is 1, by sine of the angle between the two vectors on r squared. And taking the constants outside the integral and then integrating from L equals 0 to infinity and multiplying this by 2 due to the symmetry of the problem gives us a magnetic field due to the current along this wire. So by Pythagoras, if we take this vertical dimension as z, we have the length of the radial vector squared is equal to L squared plus Z squared. So let's substitute that in here. And by trigonometry, we know sine theta is equal to sine pi minus theta, being the supplementary angle. So that will be equal to the opposite on the hypotenuse, which is Z on R. And by Pythagoras, R is L squared plus Z squared to the 1/2. So sine theta can be replaced with Z on L squared plus Z squared multiplied by L squared plus Z squared to the 1/2, which is L squared plus Z squared to the 3/2. And now if we do a change of variables by taking this angle as alpha, so tan alpha is L on Z, so we can write L as Z tan alpha, and therefore dl is Z by sec squared alpha d alpha. So therefore in the numerator we have Z squared by sec squared alpha d alpha, and in the denominator we have L squared, which is Z squared, and we'll factor out Z squared. So we have tan squared alpha plus 1, and that's raised to the power of 3 on 2. And by the following trig identity, being cosine squared alpha plus sine squared alpha is equal to 1. If you divide by cosine squared alpha, you get 1 plus tan squared alpha is sec squared alpha. So therefore, we replace this expression by z squared to the 3 on 2, which is z cubed, and sec squared alpha to the 3 on 2 is sec cubed alpha. And note that because we're integrating over alpha, we change the limits of integration. So in this case, as L goes to infinity, alpha approaches pi on 2, or 90 degrees. And z does not change with alpha. So z squared on z cubed gives z in the denominator. So we can take this outside the integral. And sec squared on sec cubed alpha is 1 on sec alpha, which is cosine alpha. So we can rewrite this integral as the integral of cosine alpha with respect to alpha. And now if we evaluate this integral, cosine alpha gets evaluated to sine alpha, and we evaluate this at alpha equals 0 and pi on 2. So therefore this integral evaluates to 1, and the magnitude of the magnetic field is the magnetic permeability by the current on 2 pi by z. And the magnetic field vector points out of the plane based on the direction of the current. A wire is bent into a line of length L and semicircle with a radius r. And it carries a current I as shown. Find the total magnetic force exerted on the wire by the magnetic field B, which points into the screen as we can see. So the magnetic force is the integral of the current by the cross product between a differential length of the wire and the magnetic field. So let's take the magnitude of the differential force as I by the magnitude of dl by the magnitude of B by sine of the angle between the two vectors. So we have a differential vector along the length of this part of the wire and a magnetic field vector goes into the screen. So these two vectors are perpendicular, and by the right hand rule, the differential force vector is going to point in the vertical direction. So given that sine pi on 2 is 1, and if we integrate both sides over the length of this straight part of the wire, then we get the magnitude of the force being equal to I by L by B, acting on a straight segment of wire. Now if we take a differential length vector along this semicircle, being dl, the magnetic field vector at this point goes into the screen. So therefore the angle between these vectors is 90 degrees. And by the right hand rule, the differential force vector is going to be perpendicular to this semicircle at that point. And now we'll draw a line to the center of this semicircle, which has a radius r. So we'll take this angle as an angle alpha. And note that if we have a differential force vector on the other side of this semicircle, the horizontal components are going to have the same magnitude, but the opposite direction. So by the symmetry of the problem, only the vertical components of this differential force vector are going to contribute a net force on that semicircle of wire. So what we're going to take is dFB, which is I by B, by the differential length, which is going to be R d alpha, by sine alpha, to get the magnitude of the vertical component of that differential force vector. And if we integrate both sides, we get the total force on that semicircle, and we're going to integrate from alpha equals 0 to pi on 2 by the symmetry of the problem, and multiply by 2. So we get IB by r sine alpha d alpha. So let's take the constants outside the integral. So we have 2IB by r, and sine alpha evaluates to minus cosine alpha, which will evaluate at alpha equals 0 and pi on 2. So cosine pi on 2 is 0, and minus cosine 0 is 1. So therefore the net force on the semicircle is 2IBR. So the net force on the wire is equal to ILB plus 2IBR, and this net force is directed upwards.